For decades, engineers have dreamed of trains that fly, not in the sky, but above the tracks. On paper, these magnetic levitation trains shouldn't even work at these speeds. Air resistance, track alignment, and power demands create barriers that make conventional trains max out at around 200 miles per hour. Yet today, experimental maglevs are hitting 620 miles per hour in test tracks. How is this even possible? Visual, slow-motion footage of a maglev train hovering, with a graph showing conventional train speed limits versus maglev test speeds. The world's cities are growing, air travel is congested, and even planes struggle with efficiency over short distances. High-speed ground transport is more than a novelty, it's an economic imperative. A train that can travel from New York to DC in 30 minutes or Beijing to Shanghai in under an hour would revolutionize logistics, commuting, and supply chains. Visual, animation showing population density, highway congestion, and crowded airports. But to reach these speeds on land, engineers face a fundamental problem: friction. Conventional steel wheels on rails create drag and vibration that not only limit speed, but also wear down tracks rapidly. Enter the laws of physics. Magnetic levitation eliminates contact friction by floating the train on powerful magnets. But that's only half the battle. At 620 miles per hour, air resistance, which grows with the square of velocity, becomes the dominant force. The energy required to push through the air scales cubically with speed. In other words, doubling speed can require up to 8 times the energy. Visual, CFD, computational fluid dynamics, simulation showing air flow around a train, highlighting boundary layer separation and turbulent wake. Vacuum tube transport takes this one step further. By removing most of the air from the tunnel, you reduce drag by 90% or more. Suddenly, speeds once thought impossible are feasible. But keeping a near vacuum over kilometers of track isn't trivial. Even small leaks can create catastrophic drag spikes. Visual, cross-section of a vacuum tube, showing air evacuation pumps and train inside. So how do engineers actually make this work? First, superconducting magnets allow stable levitation with precise control, reducing wobble and energy loss. Second, aerodynamic shaping minimizes drag, with noses so long they look like aircraft fuselages. Third, real-time control software actively adjusts levitation height, propulsion, and stability at millisecond intervals. Visual, exploded view of superconducting maglev bogie, highlighting levitation coils and control electronics. For vacuum tubes, the challenge is maintaining low pressure. Engineers use segmented tubes with pumps every few hundred meters, and magnetic propulsion that pushes the train forward without physical contact. Essentially, it's a maglev train in a near vacuum, combining two extreme engineering solutions. Visual, time-lapse animation of a maglev train accelerating in a vacuum tube, showing near-zero air resistance. Of course, nothing comes free. Energy consumption is massive at first, infrastructure costs are astronomical, and even minor misalignments or magnetic field errors can cause failure. Maintaining a vacuum tube over hundreds of kilometers is also unprecedented. Thermal expansion, seismic shifts, and air leaks are constant engineering headaches. Visual, animation showing tube sections expanding due to heat, small leaks forming, and maintenance crews inspecting. Even if a 620 miles per hour train can run, ticket prices would likely be high at first, and retrofitting existing urban corridors is near impossible. In essence, the physics works, but economics and logistics are the real bottlenecks. So is this the future of transport? Technically, yes. Maglevs and vacuum tubes can outperform both conventional trains and short-haul flights. But widespread adoption depends on cost, safety, and political will. For now, these systems are more likely to appear as specialized corridors rather than replacing the global rail network. What we're witnessing is a human obsession with speed, constrained by the immutable laws of physics, and yet, slowly bending them with ingenuity. It's a reminder that while nature sets the rules, engineering continually finds creative ways to play the game. Visual, slow pan out of a futuristic maglev tube network map overlaying a modern city. If you enjoyed this deep dive into future transport, check out our video on how Hyperloop could reach 800 miles per hour, and don't forget to subscribe for weekly engineering insights.